Hello, everybody. Welcome back to another discussion in dynamics. Today we'll start a new topic. As you can see, today we'll start work energy methods for particles. That means that we officially are done with this chapter, right? Kinetics. And this is where we are on our timeline. Okay, so plan for today is following. We will start with a brief lecture review. Then we'll do one example. And then if time allows, we will do quiz 2 overview. Okay, this is plan for today. So let's do brief lecture review. So what I would like you to imagine is the same particle, actually, the same particle as we were dealing with before. So that particle is following this trajectory. That particle P has mass m. And I also would like you to imagine that there is some force acting on our particle, force F. Actually, this red vector, that red vector F, is sum of all the forces acting on our particle, okay? So this will be net force. And my goal today is to start with F equals to ma and derive for you work energy expression. Okay, so we will start with this expression, F equals to ma. But before our derivation, I would like to ask you a question. So, okay, we know that F equals to ma is true, right? And we just took it for granted, yeah? Can any of you tell me why F equals to ma is true? I know it's true, but the question is why? Anybody want to join discussion? Yeah, Jayden? I understand, yeah. This is one answer, and what you basically did, you read that equation for us. Do you see? You didn't tell us why this is true. You just said because F equals to ma, and 2F equals to 2ma. This is you said. And 3F equals to 3ma. This is what you said. Yes. We know that, yeah. But why? Anybody want to join the discussion? Even with a bad answer. I really yeah. Sophia, you're looking at me. You want to say something, I think. So let's say that you don't have, do you want to say something or you don't want to say anything? Yeah. If you say something, I will give you 26 cents. Yeah. Do you want? Yeah. How about you, Sean? Do you want to join the discussion or you just want to sit there in silence? Second. Huh? Okay. This is closer. This is closer to the right answer, yeah. Especially word experimentally. Okay, so you earned 26 cents because you said yeah. So I'm gonna give you 25 and 1. Bravo. Okay. Anyway, yeah, the answer is that I don't know actually why they are true. I just was hoping that one of you will explain me finally why F equals to ma is true, because I don't know. Like, it is true. This is how our world looks like, but why? I have no idea. Yeah. So okay, I just was hoping that finally somebody will tell me. But anyway, yeah, this is true, of course, when velocity is much smaller than speed of light. Yeah. When velocity approaches speed of light, this is no longer true. Yeah, but at the velocities we are moving with, in this course, this is very good approximation on what's happening there. Yeah, this is how our world works. This is how our world is built. But why is it built like that? I don't know. And the word experimental was a very good idea. It was a very good choice because, yeah, it was measured by somebody called Isaac Newton, and he created that law. And he said, look, our Earth obeys that law. But he didn't say why. He just said that it obeys such law. Okay, I hope I clarified something. I made myself even more confused, to be honest, but okay. So anyway, how to derive work energy method? So I would like to project F equals to ma on our path. Okay, I'm gonna project F equals to ma on our path. So ds is obviously the vector that is tangent to the path. Okay, and I also would like to consider the motion from certain point A to certain point B. Okay, we know where our motion starts and where it ends. Okay, so we will focus on motion between points A and B. Okay, so what do we have in here? F times ds is equal to ma times ds. Okay. And now I would like to define ds even further. So ds vector, since it's tangent to the path, we can express it as ds ut, right? It's tangent to the path. It's aligned with ut. A vector-wise is at ut plus an un. Do you mind if I ask you for help again? Yeah. Could you please tell me what is this dot product just by looking at these two vectors? Yeah, just by looking at this dot product, what I should write in here. Sophia, you are again looking at me. You know the answer. I think you know the answer. Yes, it is exactly ATDS. Perfect. Sorry for the ATDS. Exactly. Okay. And I would like to. We can express AT in two different ways, guys. If you remember, yeah. AT is either dv dt, or it can be expressed as v dv ds. So in this case, we don't care about the time. We don't care how much time the motion takes. Okay, we just know that we want to move from point A to point B along the path, along that distance. So we're gonna go for this definition. Okay, so that means that if I plug this in here, we will just end up with v dv. I hope you guys can see it. Okay, so now we have f times ds, and this is equal to v dv. And I want to integrate from point A to point B. I want to integrate from beginning to the end. So the expression on the left-hand side, this is definition for work. So this is work of force F. By definition, yeah. So if we want to put it in a more mathematical way, we can actually write u12 of F, or simply u12. And this expression I must integrate. Have I forgot about m? I think I forgot about m. Yes? Sorry. mv. So in here we must integrate. In here we will end up with, I believe, 1/2 mv squared from point A to point B. And this will be equal to 1/2 mva squared minus 1/2 mvb squared. So clearly, this expression is kinetic energy at the beginning, and this is kinetic energy at the end. These are kinetic energies. By definition. So you can see, guys, that I actually ended up with such expression. u12 is equal to T1 minus T2. The other way around, yes? Oh, sorry, the other way around. T2, T1, and in here I should have B, and in here I should have A. B in here and A in here. I'm sorry for that. Yeah. So 2 in here and 1 in here. So yeah, indeed, we obtained exactly what is in the top right corner. We ended up with T1 plus u12 equals to T2. Yeah. So the take-home message from this derivation is that work energy method can be obtained via F equals to ma projected on the path, right, and integrated from the beginning to the end, from point A to point B. Okay, they are equivalent, in other words. Yeah. I just wanted you to show you that they are equivalent. Yeah, they are not like two separate objects. Yes, that we describe the motion with. Yeah, they are actually very similar. Yeah, just work energy is an integral of F equals to ma. Questions? Okay, before we move forward, I would like to focus a little bit on this dot product, F times ds. Actually, this dot product, F times ds. So, what is exactly F times ds? F times ds. I think that if we have such two vectors, vector F and vector ds, and we define angle in between them, let's say angle gamma, that dot product will be F ds cosine gamma. Is that true? I think so, yeah? So now let's focus on 3 different cases for 3 different gammas, okay? So let's see what will happen if gamma is equal to 0 degrees. Let's see what will happen if gamma is 90 degrees and gamma is equal to 180 degrees. So in this case, we have F pointing this way and ds pointing this way. In this case, we have F pointing this way and ds pointing this way. And in this case, we have F pointing this way and ds in such way. Okay, guys, so what is cosine of 0 degrees? 1. I see. So in that case, we have F times ds equals to F ds, basically, yes? Cosine of 90 degrees is 0. That means that in this case, F times ds will be 0. So work of such forces will be 0, as you can see. And also cosine of 180 degrees is minus 1. And in that case, our work of such forces will be negative, yes? The energy will be dissipated from the system. It will be minus Fs, Fds. Okay, and now easy question to you. Can you please give me an example of such force? Which which force forms 180 degrees with displacement? Yeah, it's friction, exactly. So work of friction will be negative, right? It will dissipate the energy. Okay, any questions? So I think that with that brief lecture review, we are ready to solve example number 1, if you don't mind. Let's do it. Let's do it. Okay, so as usual, just take a couple of seconds to read and understand the problem statement. Alrighty, what do we have in here? So we have a particle. Our car, we're gonna model it as a particle, and initial velocity of our car is vc. Our car goes down the incline of theta 10 degrees, and all of a sudden, our driver hits the brake. Yeah, he hits the brakes, and basically it will cause our car to stop because of the friction between the tires and the ground. And what they ask us for is how long is that distance s that takes to stop the car. Okay, we have to find that distance s. Okay, so here's how I will solve that problem. Solution. Okay, so I'm just going to take the equation we just derived. Okay, I'm just going to take that equation, T1 plus U12 is equal to T2, and I'm just going to find these three quantities: T1, T2, U12. Okay, and once we find them, problem is solved. Yeah. So I don't know. Anybody want to help me? What is kinetic energy at the end? What is T2? Olivia? It's 0. Yeah, because car stops. Yeah. At the beginning, what is T1? James? Yes. 1/2 VC. 1/2 M VC squared. Okay, so thanks to Olivia and thanks to James, we have 67% of the problem done because we found these two values. Now let's do remaining 33%. So what is work of forces acting on that system? In order to find work of forces, I think that first we should know what forces act on our system, right? So I hope that you don't mind if I draw a free body diagram. Yeah, I want to draw a free body diagram here. So it will be FBD, and we'll have mg acting this way. We definitely have normal force acting this way, and I believe that there is also friction acting that way. So we can write in here that we have three forces acting on our system. We have work of mg. We also have work of friction plus work of normal force. Okay, but let's put it in more mathematical way. Okay, so this will be u12 of mg plus u12 of friction plus u12 of normal force. However, let's put it in even more mathematical way. Why not? Let's put it in that integral form, okay? So this will be integral of mg times ds. And what will be the integral bounds? Let's keep their a and b for now, okay? A and b. Later today we will just replace them with some values, okay? For now, a and b, beginning and end, plus integral from beginning to end, tf times ds, plus again integral from beginning till end, n times ds. Okay, so all of a sudden we have ds in our equations, yes? Let me maybe introduce that ds on the FBD. So I believe that this is the trajectory of our car, yes? This is the trajectory. And I think that the displacement is going to point this way. I believe so, yeah? ds will have this direction, right? I believe so. Okay, so let's maybe solve the easiest integral in this course. Can any of you tell me what is the value of this integral? Sean? Yeah, and why? Exactly, yeah. And basically you use the information from the previous board, yeah? Yeah, exactly, yeah. So this is 0. That entire integral is 0. And why? Because n is perpendicular to ds, yeah. By the way, I believe that in this course, work of every reaction force, for example, normal force, will be 0. Yeah. In this course, I think like 99% of the time, work of reaction forces is 0. Yeah. So just keep it in mind. Maybe it will speed up your solution during the exam or something. Yeah. Yeah. In other words, in this course, we are dealing with so-called smooth constraints. Yes. That's what work of smooth constraints is 0. Yeah. You don't have to remember that expression. Yeah. But anyway, thank you, Sean. Okay. And how about two other forces? I'm afraid that they are not perpendicular to our displacement. Yes. I'm afraid that we must solve these integrals somehow. Okay, so how about we just figure out, let's focus on mg first, okay? So let me maybe express mg in such two components. One that is aligned with ds, and the other one that is perpendicular to ds. And I believe that if theta was here, that means that theta must be here as well. So that means that this component is mg sine theta, and this component is mg cosine theta. Okay, so we can ignore the cosine component, right? Because it's perpendicular to ds. So I believe that this integral will be integral of mg sine theta ds, yeah, from a to b. How about tf? Tf is already aligned with the ds, right? But it points in the other way. So here we will have minus tf ds from a to b. And let's maybe express that TF in more civilized way, okay? So I think that we have kinetic friction case in our system. Kinetic friction. So TF is equal to mu kn. So that means that TF is equal to mu k mg cosine theta. Okay, we are almost there, guys. So right now let us write mg sine theta ds plus negative mu k mg cosine theta ds. What are the integration bounds? I believe that there are from 0 to s. Yeah. If you look at the top right corner, 0 is here and s is here. So we can put 0 and s in here and 0 and s in here. And also please observe that these integrands are constant. So we can basically write mg as sine theta minus mu k mg as cosine theta. Or even we can simplify it. mg times s sine theta minus mu k cosine theta. Oof. Okay, we are done with work of forces. This is our u-12. Any questions about what happened on the board? We will. This is not the end of the problem. Yeah. Okay, but anyway, problem is done, yeah, because we found these three guys. So 100% of the problem is done because we found T1, we found T2, and we found U12. Yeah, and the rest is mathematics, Olivia. Yeah, now we are just going to take these three guys and we're just going to plug them back into our original equation. Okay, so let me steal this one. I think that T1 had this expression, 1/2 mvc squared. Ut is this expression, mg as sine theta minus mu k cosine theta. And T2, you guys told me that it's 0. Okay, m's cancel out. And this is what Olivia asked us for. She said that we must find s, and we're going to do it. And I think that this is equal to minus vc squared divided by 2g sine theta minus mu k cosine theta. And we know every value of the coefficient on the right hand side. So if you guys plug in values there, you will obtain that s is approximately 19.486 feet. Any questions? Have I lost you anywhere? Oh, yeah, it was fine. Yeah. So anyway, yeah, this is how I solve such problems. Yeah, I just write down the equation we just derived, that T1 plus U12 is equal to T2. I found these three things. I plug them back in, and the rest is mathematics. Yeah. Okay. So, Mike is yours. Was it good? Yeah. Okay. So, what now? Quiz 2. Do you want to do solution for quiz 2? Okay. So before we do quiz 2, I mean, okay, I can show this one first. Okay, so this is problem statement for quiz 2, but you guys already read it, yeah? So we can dive straight into our solution. But there are some people who are watching this on YouTube, so in case you're watching that on YouTube, this is the good moment to pause the video and read the problem statement because we are about to start solving it. Yeah, before we start solving it, I just want to go back to the intro board, yeah, because this quiz belongs to this chapter, right? This quiz is in kinetics, not work energy, yeah? So that quiz covers kinetics, and here is the solution to quiz number 2. We still have like 15 minutes, yeah? So I think I am able to solve it in 15 minutes, yeah. So what do we have in here? Aha, we have two bodies this time, yeah? Two bodies, yeah? So we have body A and body B, and they both have mass m. They are connected with the cable also, right? You can see that cable here. You all can see it, yeah? But this die has only one cable attached to itself, and this die has 4 cables attached to itself. What else do we know? We know that our system is at this configuration, yes? By configuration, I mean that this theta is, I believe, 30 degrees, yes? And at this configuration, our body has velocity v0. And there is a friction between the cylindrical surface and body A. And they ask us to find tension in the cable. So T is not known. And this is how I would solve it. Solution. So I'm just gonna follow my recipe. I told you like 7 times this semester already, yeah? So I'm gonna start with FBD for body A, let's say. FBD for A. And KD. So we have our rectangle in here. We have our rectangle in here. What forces act on our body? Definitely there is mg. There is definitely normal force. I think that there is also tension in the rope, and there should be also friction, TF. I don't see any other forces acting on this system. How about KD? What is the trajectory? Is it a straight line? No, it's a circle. Yeah, so this is our trajectory. This is our trajectory. So we must go for one of the curvilinear coordinates we were talking about this semester, yeah? Either NT or polar coordinate system. I want to go for NT coordinate system. So I'm going to go for NT. So definitely MAN points this way. And definitely, I don't know, MAT points this way. I don't know. I assumed this motion, this direction of acceleration as positive. And that's it. Now sum of forces. So EOM, equation of motion, sum of forces in the t direction, and sum of forces in the n direction. Okay, so we have mg. I have to project mg quickly, right? So mg acts this way and this way. Theta is, I believe, is here, so that means that theta is here, and that means that theta is here. So this guy will be mg sine, and this guy will be mg cosine. So clearly I have mg cosine acting this way. No, sine, that's what I'm talking about, mg sine. Minus t minus tf, and this is equal to mat. How about n direction? I have mg cosine acting this direction and n acting in a negative direction, and this is equal to man. Okay, so in curvilinear motion, we can also replace man or an with v squared over rho. Yeah, but in our case, this is equal to V0 squared, yes, V0 squared, and rho is constant, yeah, rho is R. Okay, so we ended up with such equation. So we have these two equations. V0 over R squared. And I believe that from this equation, from the second equation, we can actually find n. So n will be equal to mg cosine theta minus m v0 squared r. And if you plug in values there, you will obtain that n is approximately 15 newtons. Yeah, every single parameter on the right-hand side is known. We know the value of every single parameter on the right-hand side. Okay, so from that moment on, n I consider as known value. Okay, let's have a look at this equation right now. How many unknowns do we have in here? AT is not known, friction is not known, and T is not known. We need two more equations, yes, because we have one equation and three unknowns, yeah? So why don't we go for the FBD for the other body, okay? Let's do that. Quickly. FBD for body B. So there we have such rectangle, and definitely it has mg pointing downwards, but I honestly forgot how it looked like. Yeah, can I copy this drawing here? Oh, it has four ropes attached to it, to itself. Yeah, so we have basically such two pulleys here. Yeah, and we will have four forces pulling up. So we have 4T. And since I assumed that this guy goes this way, I'm going to assume positive direction this way, okay? MAB, let's say. Okay? And now I'm able to create additional equation. So equation of motion will be sum of forces in the y direction. And this is equal to 4T minus mg. And this is equal to MAB. Cool, so we have one extra equation. Let's see if that helped in our solution, yeah? So let's recap, in other words. Let's recap. So we have this equation with three unknowns, and we have this equation with how many unknowns? 0? No. Unfortunately, we introduced one more equation with one additional unknown. So we have two equations and four unknowns. Not good. But we need to find two more equations, right? Excuse me for a second. It was fine. Even in front of the British Queen, you can blow your nose. That's true. Oh, you know that, yeah. Okay, so we need two more equations, yeah. So I believe that most of you have in mind one equation right now. Equation for friction, right? Yeah. So we can go for kinetic friction. Kinetic friction, which is mu TF will be basically mu Kn, yes? And n we found, n was 15. Do you remember? So this will be mu K 15. Okay. So all of a sudden this guy is known, right? So we need one more equation, and that will be kinematic constraint. Yes, because if we have a look at this drawing here, if we have a look at this drawing here, I hope that all of you can see. Maybe I can make it even larger. Sorry for that. So you all can see, hopefully, that this guy has attached one rope to itself, and this guy has attached has four ropes attached. So we can basically write such an expression: A T is equal to, I believe, 4AB. Yes. So basically, due to this rope, this is the kinematic constraint that occurs that relates the acceleration of these two bodies. Okay, that's it. We found 4 equations and 4 unknowns. So this is not 2 anymore, but 4. So this is solvable. Okay. So if you want to solve it, you can obtain that your tension in the cable, is equal to 1 divided by 17 mg sine theta minus mu km plus 4 mg. And if you plug in values, you will obtain that your tension is equal to, this was 15, right? This is equal to approximately 4.752 newtons. Okay, guys, that will be my summary of quiz 2. Questions? Yeah, I don't see any, but I will hang out like for a couple of minutes after the discussion if you want to talk. So thank you for today, and I hope to see you on Friday. Bye.